Thank you for coming to the seminar. I'm Jillian, and I'm going to talk about some simulations that I have done about tracing where the gas that black holes accrete comes from. So I've just submitted this paper. It is on AstroPH as of last Thursday, and I'm especially interested in comments from the observers in the audience because I have talked to almost no observers about this, and I feel like my future presentations and perhaps the paper itself may be improved by whatever you guys might have to say. And so I'm really interested in the things that you want to know and the things that I can answer based on that. So feel free to chime in. All right. So as Mike asked, is this a real galaxy or a simulated galaxy? It is a simulated galaxy. And it is at Redshift 4, but I pretended it wasn't at Redshift 4 when I made this image, so I took my telescope right next to it, and because then you can get a much more pretty picture than if you actually pretend that you have billions of years of travel time in between us and that. So this galaxy at Redshift 4 is about, the disk size is about 5 kiloparsecs or so, and this bar is like 1 or 1.5 to give you an idea of the scale. So the questions that I want to answer: what do black holes eat? Well, for the most part, it is gas. They eat some stars here and there. They do merge with each other. I'm going to ignore those things for this particular talk. I can give another talk later on something else, but this is the gas talk. So what I want to know is, where does this gas come from and how does it get to the black hole? So one of the strong paradigms for the brightest quasars at the highest redshift are that you have a bunch of gas-rich galaxy mergers and they all smash together, and all of this gas funnels to the center of your galaxy. You get your black hole quasar shining enormously. And so one paradigm is that these major mergers trigger a lot of black hole accretion. And for the brightest things at the highest redshift, that's probably true. But what about lower luminosity AGN, and what about things that aren't in mergers? One thing in particular I've been trying to focus on is, what is the role of cold flows? So a few simulations recently have showed that it's possible that gas flowing in from the sort of ambient universe through filaments can possibly directly fuel a black hole without having a bunch of merger activity. Because at high redshift, you have lots and lots of inflowing cold gas that, if it hasn't been torqued very much because your galaxy is still small, there's not a lot of angular momentum yet, the streams can just feed the black hole directly. And so what I'm wondering is, what is the comparative role between cold flows and mergers, and does it depend on redshift, on galaxy mass, on gas fraction, on merger rate, on all of these things? So I'm not going to answer every single one of those questions today, but this is sort of the first step in what I think of as a series of studies that I'm going to do focusing on this topic. So what I'm going to study is the relative role of cold flows and mergers in feeding black holes in high redshift galaxies. So I'm a theorist, and so I know that when in my simulations, gas comes from somewhere, whatever this thing is, and ends up here where my black hole is. But because I'm a theorist, I have a simulation. It traces through all of time. I can rewind it and trace the gas backwards. Oops, did it just go back? Trace the gas backwards and determine where it came from. So this is basically what I'm going to do. I run my simulation. I have a black hole in the center of my galaxy. This is a cosmological simulation. So the black hole that happens to be in the center is my one that I care about. And I identify the gas that this black hole accretes and then trace it backwards. So how do I decide how it is accreted? So in my simulations, I use the Bondi-Hoyle accretion prescription. And we all probably know that that is not a good way to model accretion. But in a cosmological simulation, there's not a lot of other good ways to model accretion. And for this study that I'm talking about here, I'm not so much worried about the absolute gas accreted and the absolute masses of the black holes and what feedback is doing, but I'm more interested in the relative contributions of gas from different origins. And so what Bondi-Hoyle will tell me is which gas comes close to the black hole at what times and has the sort of properties that would want to be probably accreted by the black hole. And so that tells me enough about, because then I can, once I identify that gas, I can trace it backwards. And so whether its a precise accretion rate is exactly right isn't as important as just being able to identify the gas properly. So today, Bondi Hoyle will be all right, I think. Yeah?
Do you have to multiply the Bondi accretion rate by the factor of 100 or a few hundreds, like other people did?
I do not do that. I multiply the Bondi accretion rate by 1.
By 1?
Yes. Well, it depends who you talk to.
But people show that just the regular Bondi accretion rate is not enough to account for the first growth of black holes in
So that's true. So part of that, I think, is resolution dependent and code dependent. So the people who multiply the black hole accretion rate by 100 or 1,000, for one, they're using Gadget and I'm using gasoline, which for the most part, zeroth order aren't that different. But when it comes down to the differences between the interstellar medium modeling and the higher resolution that we are able to get with gasoline by the way that we do things slightly differently, I've found that if I multiply my accretion by any number larger than 2, I end up getting an enormous black hole and then blowing up my galaxy with feedback. And I don't get anything that resembles a real galaxy. And the galaxies that I'm showing here and the more like low redshift Milky Way analogs that I simulate actually look like realistic galaxies and have pretty reasonable growth rates. And so I am pretty satisfied with not multiplying by 100.
The gas that you have around the black hole, maybe the gas that you have in your simulation is colder, and that's why the accretion you get is...
Yeah. The gas in our disk galaxies does tend to be colder. We get thinner disks than what you get with Gadget because they have a multi-phase medium, so all of their gas has a hot piece to it, I believe. I'm not a Gadget expert, so if I'm saying something wrong, feel free to chime in. But the way we model an interstellar medium, I believe, is more realistic. I'm biased, but it's more realistic. All right. So I'm going to give a few standard definitions here. This is probably stuff you all know, but for this study, I have defined the accretion in specific ways, so I want to make sure that's clear. So as gas accretes onto a galaxy from the ambient medium, if that galaxy is massive enough, when the gas reaches the virial radius, the gas tends to undergo a shock, and shock heats to the virial temperature of the halo. And then eventually the gas works its way into the galaxy, but that may take a while because cooling times are fairly long. So I'm using the prescription that Alison Brooks used in her 2009 paper to identify shocks. So basically there's a temperature and an entropy increase when we see the gas crossing this threshold, and so if we see the temperature and entropy increase, we mark this gas as shocked, which is going to be red in all of my plots in this talk. So gas doesn't always shock, so if your galaxy is small, it's not massive enough to support a shock, so about 10 to the 11 in virial mass is about when shocks start to happen, although it depends who you talk to. And so sometimes if your galaxy is small, like if it's a high redshift galaxy or a low mass galaxy in the local universe, you can just get this gas directly. And so this is the gas I'm going to call cold flows, or unshocked gas, and it's going to be blue in this talk.
The cold flows probably got shocked outside of the virial radius, right?
Possibly, but we don't.
They had to have been shocked when joining a filament of the cosmic web before making a cold flow, right?
Yeah, so we trace whether or not there's a shock around the time when it enters. So if it gets shocked at redshift 20 and then enters the galaxy at redshift 5, we still count that as I'm not sure if we could resolve something at redshift 20, but...
I thought cold flows were actually thought of more massive galaxies trying to get the gas to fall in without shocking.
So that looks like this.
Oh, sorry.
And so if a galaxy is massive and has a shock, for at least a little while after the shock develops, the filamentary structure of the gas inflows can penetrate the shock and still feed cold gas to the center of the galaxy. And so this is another way to bring cold gas in. Is this what you're talking about?
Yeah.
All right. Kevin.
Joining the scientific illustration. So one thing that I gather, I guess, just from listening to theorists argue over this, so I'm pleading total ignorance here, is that there's a debate over whether those cold flows actually make it all the way down to the galaxy where they enter this sort of diffuse stage where then other magic happens.
Right. So again, it depends who you talk to, and I think you might be referring to one of the recent Aripo papers, which reports that their cold flows sort of dissolve around here. And I'm not convinced yet that that would happen. It depends a lot on how you model things. And I think especially at high redshifts, when there's not a lot of stuff to dissolve your cold flows, I think they are really efficient at getting stuff to the center. Some other, like there's some work by Johann Dubois in France who's been doing this same sort of simulations but with Ramses, and he finds that cold flows can efficiently get to the center till about redshift 8, and then the streams start getting torqued. Yeah. And the streams start getting torqued because the galaxy picks up some angular momentum, and then they sort of start to disrupt. So I think it depends on how you simulate it, and I think that that's definitely an unanswered question right now. So.
But I do agree with the point that maybe most of the debate happens at very low redshift. The biggest differences between an SPH type of prescription and these more AMR type prescriptions, that difference starts well after this study, more like redshift 1 to 0. So
yeah.
Things are pretty similar between the two types of simulations.
Yeah, I can comment more on that outside of this talk if you like, but I think I'll go on from here. I have a lot to say about it, though. All right, so the other way for a galaxy to get gas, of course, is through galaxy mergers. So if you have small galaxy plus other small galaxy, you make a big galaxy, and it will also deliver a lot of gas. And so I'm going to refer to gas that used to be in another galaxy and now comes to my main galaxy as gas that is coming through clumpy accretion, and that's going to be green. So to summarize, we have cold flows, either that will enter in low mass galaxies or through filaments. We have shocked accretion, which will happen if your galaxy has high mass. And we have clumpy accretion, which means that it came in through mergers. Are we good? All right. So now that we know how galaxies get their gas, we can talk about how black holes get their gas. So what fraction of these accretion modes feeds the black hole most efficiently? So to study this, I have run 3 simulations, and I'm going to show you a movie of one of them. It's the requisite theorist movie and the theorist talk. So what we have here in the early universe, we have gas, which is this gray, floofy stuff. And it is condensing to form proto-galaxies. And so you can see the filamentary structure here. These bright blue bits are young stars. And as the stars age, they will turn red.
So the streams we see going in are the cold flows. Where on that scale would be the virial radius?
Oh, maybe about this. Maybe out to here or so.
Is that a shock that just literally flashed by?
That was, I think, a black hole accretion event. There's a mini explosion that happens at very high redshift. So you can see that a lot of gas is streaming in from cold flows throughout the history of this galaxy. And there's also a bunch of little mergers going on. So earlier on there were some more major mergers when everything was still very tiny, and now there's more just some little things floating by. There's another one coming in over here, but it doesn't get there by the time we hit the end of our simulation. This is redshift 4. So I've run 3 cosmological simulations, which are actually much larger than the screen, but the movie just zooms in on the primary galaxy, which is the only one I'm going to talk about today. So I have 3 simulations of galaxies that are fairly similar to this one that I've run to redshift 4.
Comment on at the start and the end of your movie, how far in like time or redshift have you modeled?
It starts at redshift 99 and goes to 4. The spatial resolution is 250 parsecs. So I have three galaxies, which I've creatively named HC2, 3, and 4. And what we saw was the movie of HC2. And so what I have here are simulated images of each one edge on and face on using the Sunrise radiative transfer software. So these are SDSS GRI band simulated images. I didn't include any dust, so it's possible that they could be a little redder or a little fainter than what you see here. But for the most part, you get the idea that they're sort of disky. This one has a bar in it. This one is actually much smaller than the other two. And for the most part, I'm going to ignore it for the rest of the talk because its black hole does not actually do much of anything.
Looking for a very brief answer about the radiative transfer. At what do you finish the dynamical simulation and then you reprocess the?
Yes. If we feed the radiative transfer software a simulation output, it calculates star formation histories based on an IMF and stellar ages and metallicities, and then does the radiative transfer through the existing gas in the simulation. And then I spin it around and make different images of it.
Gas gets to include gas, dust, it produces the dust?
Yes, it produces the dust based on the temperature and metallicity of the gas.
Are the black holes created the same way in your previous work, where you have zero metallicity plus star formation conditions equals black hole?
Yes. So there's actually more than one black hole in these galaxies. They each have a central black hole, but they have probably on average of 20 or so black holes also roaming around in the halo, which are for the most part doing nothing. But those black holes were either formed in a non-central region or they were brought in through mergers from other galaxies. But I'm not going to talk about those, even though they're really exciting.
Are they a lot smaller than central black hole, or are they comparable?
They all start out at the same mass. So the seed mass in this simulation is about 10 to the 5 solar masses. And so I can't resolve anything smaller than that. But the central black holes grow to a few times 10 to the 6. So they reach equilibrium with their galaxies and accrete a lot of gas. And the ones out in the halo don't accrete any gas really because they are not in a place with any gas. So they just sort of hang out and are dark. Amy.
Talk about each of these four, but I'm just curious. So that one has a black hole in it, but it's just not accreting? Is that right?
Yes.
Is it in the middle of the galaxy, roughly?
Oh, it's close to the middle. Yeah. I also don't fix the black holes in the center. I allow them to dynamically evolve as a black hole would normally be expected to do, rather than being forced in the middle. And so sometimes the black holes slosh around the centers a bit, and that's happening in this one. If we look at some characteristics of these galaxies, so HC2 and HC3 both have stellar and gas masses of a few times 10 to the 10 solar masses, and HC4 is smaller by an order of magnitude or so, which is probably has a lot to do with why its black hole is less exciting. I've given you some magnitudes from Sunrise, even though I don't know.
It's very luminous because there's lots of young stars.
Yes, there's a lot of young stars. And they're really, really blue. So they're pretty luminous. I looked up a Redshift 4 luminosity function for Kevin, and these guys are beyond the knee of the luminosity function, so they're on the bright edge of it. And this one is around the knee or a little bit on the other side.
This includes only
Yes, this is just luminosity from the stars. So these are basic characteristics of what they look like. Yeah?
Cool gas. The gas there is mostly H1.
So this is the gas within the entire virial radius of the galaxy. So it includes hot halo gas as well as the cooler disk gas. Not off the top of my head, no. I can check it, but. Okay, so what I wanted to figure out, especially after talking to Kevin, is can you observe these as AGN? And the answer is probably nope. So what I've got here is bolometric luminosity versus time, and I have Redshift here up on the top. And these hatched regions are where mergers are going on. So major mergers are red and minor mergers are blue. And there's often more than one going on in this region. Like this is 2 major mergers on top of each other. So 10 to the 42 ergs per second in luminosity is right here. And so don't get all that bright. And if I overlay what Kevin gave me from his table on his upper limits for soft X-rays, you get these yellow lines right there. And this is soft X-rays, and my plot is bolometric. So if you move it up by a factor of 20-ish, this is me just drawing on my plot. But basically you can see that the luminosity of these black holes doesn't really hit these lines at redshift 6 to 8, which is where Kevin was focusing on. So the fact that Kevin does not detect any AGN in these galaxies may be because they're just not bright enough. Now Kevin and I haven't actually verified if my galaxies and his galaxies are the same, but they may be the same. If they are the same, it's okay that he doesn't detect them, or maybe it's okay that I don't say that they're detected. We agree. That's the point. We agree. And so later on in this galaxy's evolution is when it would get bright enough for a stacked Chandra sample to detect this AGN activity. But
you can have the massive black holes growing at a time, no problem. That's not luminous enough.
Yeah, they're growing. They're certainly growing, but they're not growing very rapidly at this time.
So what's the typical Eddington ratio then, 8 to 6 range?
Probably 10 to the minus 3 or less, I would say. They're not very big. I can check that up though and verify it. We should do that. Yeah, if I started with a more massive seed, it probably would go up. Yeah, but the seeds are already fairly massive. They're 10 to the 5. That's getting close to the ceiling of where we think seeds might be. Not that we have any idea, but 10 to the 5 is considered a massive seed. It's not a medium seed. So, yeah. So.
The upper panel looks like you have some limit. Is that the Eddington limit?
Yeah, it does. This does look kind of like a ceiling here. So that is likely the. I need to check that. But that is likely the Eddington limit for. No, it's a few times 10 to the 6. Yeah. Right, which is here.
What the opacity is, if it's less opacity, it could be higher.
Yeah, I have to.
It needs to be. So and the Eddington limit would. Yeah, because if it's coupling strong and electron scattering, then.
Yeah, well, I use the standard 0.1 efficiency that everyone else uses for energy conversion. So let's look into this later. I'm not sure. So if we want to look at growth in particular, so all the plots in the future are just going to be that HZ2 galaxy because it's the same as HZ3. So here we have black hole growth versus time. And what I have on this line here is the total black hole mass. So it includes the seed mass of a few times 10 to the 5. And then every time there's a black hole merger, there's a little jump. And the solid lines are the mass through gas accretion. So the black one is the total amount of mass accreted in gas. The blue is accreted through cold flows. The green is clumpy through mergers. And the red is shocked gas. And so what this clearly shows is that cold flows are dominating the supermassive black hole accretion. And also that this black hole is undergoing most of its growth after redshift 5 or so. And so redshift 5 to 4 is maybe the time that we should be for these types of galaxies to be accreting and being seen as AGN. But so dominated by cold flows. But does that mean that black holes prefer cold flow gas for some reason? Or does that mean that this galaxy is made of cold flow gas, and so the black hole is just accreting whatever it has around?
How do you distinguish between cold flows and clumpy?
Clumpy gas has at some point been in another galaxy, whereas cold flows just come from empty space.
It's based on its origin.
Yes, its origin. All right, so it turns out that the black hole preferentially accretes cold flow gas because the galaxy is made of cold flow gas. So what this plot shows is the fraction of gas that comes from cold, clumpy, and shocked origins versus redshift. And so the solid line is what the galaxy is made up of. And basically, all the time, between 60 and 80% of our galaxy has been fed by cold flows that whole time. And the black hole line follows it pretty well. That's the dashed one. And the green is our clumpy stuff. So we have some mergers that go on between redshift 10 and 8. The clumpy fraction increases in our host galaxy, and the clumpy fraction increases from the black hole. The galaxy isn't massive enough to host a shock until about here, and then we have an increase in shocked gas in the galaxy, and then an increase in shocked gas in the black hole. So basically, the black hole will eat whatever is around. So that's the point of my title. But there's no accounting for taste. Black holes will eat anything. They will eat whatever they are given. If you have a galaxy that is made of all merger gas, your black hole will be fed with all merger gas. If you have a black hole or galaxy that's made of tons of different stuff, then your black hole will want to eat tons of different stuff. And so this indicates that as gas enters the galaxy, once it hits the disk and comes near the region where it can be accreted, it just gets stirred and mixed around. And so there's no preferential thing for the black hole to accrete. It's just a big pot. Elena, do you have a question? That's fine.
How can it be otherwise? What typical process by which this could change from one of the three types?
It could change if cold flows feed the black hole directly, if they come from filaments and just go straight to the center without getting stirred up in the galaxy along the way, then you would see preferential cold flow accretion. They would have to have zero angular momentum. That's feasible in the very early universe, but not really later. Also, if the idea is that merging galaxies, if they have head-on collisions with the center, can directly supply the black hole with gas from another galaxy. If that's an efficient process, then you would see something from clumpy accretion dominating.
At that stage, the accretion of the galaxy is black hole.
Yeah, and I'm going to talk about angular momentum in 2 slides. So you are asking great questions. Tamara.
Okay. So is it fair to say that this is true down to your boundary radius? The sense that yes, black hole will eat anything at the boundary radius. But in principle, at smaller radii, you can have one phase of the gas, like for example, cold phase, may transition into a hot phase if the gas is shocked or something else happens to it.
Well, so firstly, one, I don't resolve the boundary radius, but it's definitely true to 250 parsecs, which is what I do resolve here. But what I'm tracing isn't the phase of the gas as it's being accreted, it's the phase as it entered the galaxy. And so gas that comes in the cold phase will always be called that, even if it gets shocked once it works its way to the black hole. So I'm not accounting for here how it gets to the black hole and what happens to it.
So once it gets to the black hole, it may be something else from there.
Yeah, but in terms of what the origins are, so this I would say is true to my resolution, but it's probably also, once gas is in the very center of the galaxy, it's probably not going to matter where it came from in terms of what the black hole will want to eat. Javier and then Amit.
I have a similar plot for the metallicity of the gas because you would have thought, I would have thought that the gas that is in the vicinity of the AGN or quasar is very much gas enriched. And then the cooling time is going to be very short, and therefore it's going to be the first gas to be fed to the black hole.
I have not looked at metallicity at all. That is a really great idea. I'm going to write that down.
Stars first.
Yeah. So how will it get those metals? But it can be, metals can be diffused from whatever process into inflowing gas, possibly. Metals. All right, I'll look at that. I haven't looked at it at all.
And the speed of the gas is probably going to be high. The cycle, and it's not directly coming from the cold flow.
Mm-hmm. Okay, I'm going to look into that. Thanks.
Metallicity, you're thinking not just metallicity of the origin of the gas, sort of metallicity once right
As
around the bonding radius.
Yeah, see, well, a lot of what I'm looking at now is now I know where it came from, but once it's in the galaxy, what actually triggers it to reach the center of the galaxy? I'm actually writing a proposal on this right now. As I'm talking, I'm multitasking. So it's something I'm definitely interested in. I'll look into that. So, Amit?
The black hole is not very particular about what it is. So you give him hot food, it's hot food. You give him cold food, it's cold food. But you have the boundary description, and you have the speed of sound, which I think would mean that it refers to it cold food.
Yes. Yes. So again, the cold doesn't mean what its temperature is at the black hole. It means how it entered the galaxy.
When you use the boundary description, don't you measure the temperature somewhere close to the black hole?
Yes. I do measure the sound speed of the gas near the black hole. But so from what I've gathered from so far, my tracings of the gas as it crosses the virial radius and goes to the black hole, it gets very mixed up and stirred around, and all sorts of things happen to it in between when it enters and when it gets accreted. And so while the black hole will preferentially eat cold gas, this gas is not going to stay cold, and this gas is not going to stay hot. It undergoes all sorts of physical processes in between. And so actually studying how the gas does efficiently go to the center of the galaxy is really, really hard, because there are just so many processes that are going on.
Right, I just think that it refers this means that
So you can, in principle, build histograms in temperature, and you can see what is the physical state, what are the physical properties of your gas. Different from.
Yes, it will. Yeah, it'll look different from the initial, for sure.
And I think maybe a subtle point that it took me a while to understand was that definition of cold is really sort of an origin definition. It is not the state. So there is 10 to the 6 Kelvin gas in that cold pile, right?
Yeah, cold really means unshocked. Cold means unshocked.
But
it's not a temperature criterion.
Before it entered. So it actually could have even been shocked.
Yeah.
It's just not shocked right as it crosses the virial. So this is I think that's an important thing to keep in mind. So I think a temperature plot would be awesome. A phase state.
Yeah.
Kevin?
Your simulation includes stellar mass loss and winds and things like that. And under which category does that material get counted?
That material does not get counted because it is not. It has been a star, and so this is only.
Sometimes it's subdominant, but later on it becomes important. The stuff that's lost by stars this early in the year.
Stuff that stuff that is lost by stars is in the simulation a pretty small fraction, and so the way it works in the simulation is that we take a little bit of mass away from the star particles and add it to the gas particles, along with whatever metallicity and energy is appropriate. But that gas particle still retains its identity as that gas particle, and so it doesn't have an effect. All right. This slide here is basically just a summary of everything that I've just said. So here are the Redshift 4 compositions of our entire halo, and this is what the black hole is also composed of. And so these numbers are effectively the same. And so the black holes are not picky, and they will just accrete whatever they want. They don't care where the gas came from. So then what does matter? And now we get back to Elena's question about angular momentum. It turns out that angular momentum matters. So what I measured was the angular momentum of gas as it entered the halo. So not as it's being accreted by the black hole, but as it enters the halo. So this is a cumulative distribution of angular momentum. The solid lines are the angular momentum distribution of the gas, of all of the gas as it enters the halo, and the dashed lines are just the gas that is accreted by the black hole.
How much is this in the units of the standard lambda, small case lambda, lowercase lambda?
I don't know. I have not calculated that.
No, not the ratio.
The spin parameter.
Logical spin parameter.
Spin parameter. I have not calculated it in those units. I don't know. I was just trying to do a basic comparison, and you can see that these dashed lines are all a bit to the left of the solid lines. So the gas that is accreted by the black hole has overall lower angular momentum on its way into the galaxy. And that makes sense, because if it has less angular momentum, it doesn't get as caught up in the rotational aspects of your galaxy. It can more efficiently go to the center. So this is something I'm going to be focusing on a lot more in my future work, trying to figure out how angular momentum plays a role in what gas goes where and what gas doesn't go where.
Do you expect the gas to be balanced stable in the simulation?
I do have some bars forming in the simulation, yeah. So part of that, it's often difficult to untangle the resolution effects and the bar formation. And so in my future work, I'm going to use higher resolution and also do some isolated cases. But it does go bar unstable. And, well, the disk goes bar unstable.
Seems like it's a pretty small difference, 10% or 20%.
Yeah, it isn't screaming at us. You're right. But considering that I was in the previous whole rest of the talk, everything was all the same. Now that I have a difference, I was like, I need to show this difference. Something actually makes a difference. So it doesn't matter where the gas comes from, but in terms of origin, but it does matter how much angular momentum it has. It doesn't matter a ton, but it does matter. Yeah, Richard.
Where? So does the gas that falls into the black hole preferentially come from material that's just outside the virial radius and falling in, or from 20 times the virial radius and falling in faster?
Well, it's all at 20 times the virial radius at some point. Well, so it depends when you're talking about. But I haven't done an analysis on like angles of where things are coming in or speeds. No, I don't know.
Why is it one the clumpy gas to be so much more below the typical clumpy gas?
That's a good question, and I think it's how I define when it enters the galaxy. So for the smoothly accreted gas, I define it as when it crosses the virial radius. But for the clumpy gas, it's still in its host galaxy when it crosses the virial radius. So when I say the clumpy gas enters the host galaxy is when the satellite is completely dispersed and it can't be identified as a satellite anymore. And so it's not really in the same place as the smooth gas is when I say entered the galaxy. And so I think that is the reason for the difference here. All right, so the main points that I have figured out in this work are that these massive-ish Redshift 4 galaxies may not have a ton of supermassive black hole activity, certainly not at Redshift 6 to 8 when Kevin's looking for it. Supermassive black holes in their host galaxies have the same composition in terms of origins of the gas, and incoming angular momentum probably makes more of a big deal. So the open questions we still have are what happens from Redshift 4 to 0, because I've only been studying these galaxies to Redshift 4, and obviously exciting things happen after that. Where do Kevin's galaxies fit in? Maybe what my galaxies and his galaxies are different, but if they are the same, then how does this all fit in a larger picture? When do black holes form? When do they accrete? And when do they just sit there and do nothing? And why does that happen? I want to know what the angular momentum evolution is of gas as it approaches black holes. Are there any observational signatures of these growth modes? Is there any way that we can tell if a black hole grew through cold flows or grew through merger accretion? Is there a way we can tell if a galaxy grew through cold flows or grew through mergers? I mean, some galaxies for sure, but some of them not so much. And so is there any way that we can confirm this observationally? Something I want to think about. And then what are the repercussions for the M-sigma relation? If you have a black hole that grows all through cold flows because there aren't any mergers, you can have a big black hole, but no galaxy bulge. And so the M-sigma relation will not apply to a galaxy like that. And what does that mean? And can we find galaxies that look like this? Maybe something like Henne's 210, but maybe also a bulgeless disk galaxy.
Still asking you that about this.
These galaxies do have bulges, yes, but they also have a bunch of mergers.
Actual bulges or pseudobulges?
How do you want to define bulges and pseudobulges? Yeah, they have central, bright, roundish concentrations of stars moving in randomish ways, not rotationally dominated. So I'm going to call it a bulge, but you can call it what you want.
So if you started your black holes not at 10 to the 5, but 10 to the 3, would they have done essentially the same thing, or would they suddenly have grown at the Eddington limit as fast as they can until they reach 10 to the 5 and then sat there?
I can't really answer that because I can't resolve something that would be at 10 to the 3 because my resolution limit for seed mass is my particle mass, and that's 10 to the 4, 10 to the 5, but I can't do 10 to the 3. So I can't, and also I can't resolve the gas well enough at that scale for the tiny black hole to respond appropriately to it. So I don't know. If I start with a more massive seed, then it accretes all of the gas in the neighborhood, and the galaxy is a big black hole and like 4 stars. Yeah.
Would that affect anything in the galaxy evolution?
It probably would, yes. It would have.
Talking about M simulation, that would be more interesting to think about.
Mm-hmm. Yeah. So yeah, and yes, I'm just gonna say yes.
Was I right in seeing a cumulative mass plot that your galaxies were no more than 10% of the gas?
You mean the black? Oh, the black holes. You mean?
The mass of the black hole is always like at least a factor of 5 or maybe 10 more than the total mass of the gas.
Yeah, in that particular case, the black hole is the total. Yeah, it is getting a bunch of its gas from mergers from black holes, and so.
So that's suggesting a sigma over the.
Yeah. So I'm hesitant to show this, but I have an M sigma relation plot. But it has proceed with caution on it. So this is the Redshift 4 M sigma relation. You should know that there is no Redshift 4 M sigma relation. It has not been observed at all. It is. Oh well, it is. I have not seen it. But so ignore this for now. And this line here is the Redshift 0 M sigma relation. I'm not claiming that these points should fall anywhere near it. I'm just putting it up there for the heck of it. The HC2 and HC3 black holes are these two guys. And the HC4 one is this one. And this thing here is me not being able to resolve low mass seeds. So my seed mass is here. And so I form seeds merge together, and so they get larger, and these galaxies are still really small. And so I'm not resolving this part of the M sigma relation. If seeds are massive, then this is what we'll see. Because, and Marta Voluntari and Priya have a paper that predicts this sort of plume here for massive seeds, where if you have little seeds, it continues down this way. And so if seeds are massive, you will expect these big seeds in these little galaxies, like here's Henize 210 right there, ish. So, well, oh yeah, I guess it's up here. Anyway, it's in this spot of the plot. And so if seeds are massive, Henize 210 fits in this thing. And if seeds are not massive, then this is me not resolving seed formation in the way that it happens.
What fraction of the gas goes into black holes as opposed to the galaxy? I mean, I know it's a conference on black holes, but actually some 30% still trace amount ends up in the black hole. Mm-hmm. The rest ends up in the galaxy, and it must be doing something very interesting.
It's forming a lot of stars, yeah.
A lot of stars.
Yeah.
So your simulations get that ratio?
Of?
-3, the mass of the black hole in the galaxy?
Well, it's more or less. Also, these simulations were not run with the molecular hydrogen prescription that the Gasoline collaboration has been using recently to make extra awesome galaxies. And so these sigmas may actually be a little bit too big because the centers are a little too concentrated.
It does have high temperature metal cooling, right? Otherwise
it does not have the high temperature metal cooling. Nope, no metal cooling. I haven't made this plot for higher redshifts because it seemed even more absurd than doing it for redshift 4. But, yeah, it's, well, I mean, these are kind of coming at it from this way, and these are coming at it from this way, but it's not, I don't have enough statistics for the higher mass galaxies to see a trend yet, because these are zoomed in simulations. I'm focusing on a particular galaxy, and I'm not going to claim that I can do science with this. So, Mike.
What happens with feedback?
All right. What happens? So
tell us how you deal with feedback and what affects it.
So I model feedback by dumping thermal energy isotropically in the surrounding gas, based on the, some percent of the accreted mass. I use 3%. Lots of people like 5%. 3% works well for me. I'm going to use 3%.
Centrally deposited or uniformly deposited?
It is deposited over the SPH kernel. So closer gas gets more feedback, further away gas gets less feedback to some radius.
In terms of luminosity, wouldn't star formation dominate over that anyway?
Yes. In these galaxies, star formation definitely dominates over the black hole accretion luminosity.
So the feedback is based on
the accretion rate.
Is there any star formation feedback?
Yes. It is. We model supernova feedback using a blast wave formalism, where based on the blast wave equations, gas within a certain distance from the supernova has its cooling shut off for a certain period of time. And the cooling shut off allows the gas to stay hot and expand and flow away for some period of time. And then once it eventually cools, it either escapes or it falls back onto the galaxy. Did that answer your question?
So to what extent does feedback, well, how good is the feedback? Where I'm getting is what fraction of the incoming matter is halted or expelled?
Well, it depends on galaxy mass. So the other plot I can show you about
The baryon fraction. The baryon fraction.
Yeah, so I have this plot here, which is also in my paper, of the stellar mass versus halo mass relation. This is from Moster et al. So this is done with abundance matching. And this is Moster's redshift 3.5 line here, because there is no redshift 4 line in the paper. And so, and these dashed or dotted lines are the 1 sigma range. And so my galaxies fit within 1 sigma and are characteristically above this line. And our galaxies that are run with the molecular hydrogen prescription for the ISM are really well landing on this line. The recent paper by Farah Munshi shows that really well. It's in FJ somewhere. But so basically, in low mass galaxies, we see a lot of gas being expelled by supernova feedback, and in higher mass galaxies, less so. We still have a few too many stars going on up there, but the molecular hydrogen does seem to alleviate that by regulating star formation and the feedback a bit better. And so in all my future runs, I'm going to use the molecular hydrogen prescription, but we're still getting it to play well with the black holes. They don't always agree, so I'm working on it. But overall, the baryon fractions are reasonable. I haven't measured that. I'm trying to think of my collaborators' papers. Javier, do you know if it's something that gasoline people have looked at? I don't know. I would say they're probably, I don't know. I would say they're comparable, but that's just me assuming.
A lot of folks are making that.
Yeah. Yeah, I haven't looked at it. I'm not sure.
Is it fair to say that the gas that fell in, either from cold flows or other galaxies, actually completely lost memory of where it came from, and in the end just formed some warm soup that black hole is eating, because otherwise black hole would much rather eat cold gas, as I pointed out. But the fact that it's eating the same percentage, the same ratio
Yes.
as the galaxy basically means that that gas has no memory of where it came from, so black hole cannot discriminate anymore.
Yeah, I think the gas does lose its memory of how it got into the galaxy. I mean, you can imagine, say, you have a satellite galaxy which has some enriched gas coming in, and you have cold flows that are unenriched coming in. Perhaps, if, like as Javier was saying, if something is more metal rich, it can cool more efficiently and maybe reach the center.
What about momentum-driven feedback? Would that produce more cold gas?
I do not know. I'm not going to speculate on momentum-driven feedback. Yeah, let's talk about it.
Showing plots of sources of gas for the black hole and the galaxy versus showing particularly the shock gas, there was a lag.
Mm-hmm.
The galaxy started shocking things, and of course gets a contribution right away, but then the black hole only accretes that way, presumably as it's kind of worked its way down into the interior.
Yes. Presumably that is what's going on.
Yeah, the red curves.
This is a lag. Here there's a lag. Here there's maybe a lag.
What is the lag, corresponding lag in star formation? So will you see the black hole is, growing at the same time stars are forming? Or do they form first and then the black hole grows, or vice versa?
So I have a lot of plots in the back of my talk. Here's the one with fractions of stars. So here, black holes are still a dashed line. Stars that form in the very center of the galaxy very recently are the solid line. So here I'm not doing like a cumulative fraction. This is everything that just happened in 50 million year time bins. And I don't really see a lag in the stars for clumpy or for cold flows relative to the black hole. Here there is still one. And so I think that shock gas enters the virial radius, it shocks, it hangs out there for a while before it comes down. That makes this lag make total sense. While it's hanging out, no, it's probably not forming. Oh yeah, this is stars. It must, You're right.
Not a lot of stars.
Yeah, this is not a lot of stars. But yeah, there's still a lag here.
If you saw some kind of really, if it's lying on one side or the other of the sigma relation, you can try to argue, well, that's because it hasn't caught up yet.
Right.
And that would tell you what.
Yeah. Overall, this is a really small fraction, so I would say that overall there is not a lag, that these mostly follow each other.
But it's a growing fraction with time. It'd be interesting to see what happens towards redshift 0.
Yes.
Definitely. That would be the spurious numerics with the spurious clumps that are forming when the gas is shocked. We have this SPH clumps that are really highly star forming. And I don't know if you try to remove those, because those are annoying. I mean, in the way that they are sort of coming in through cold flows as well.
Yeah.
They're spurious. So.
I didn't think of that.
And it's gas in stars coming in. So.
Yeah, but these stars that I'm tracking here are only stars that form right in the center of the galaxy. So these stars will not. Overall star formation, yes, that would be an issue, but these stars are not those. They're forming within like half a kiloparsec of the center.
But that's only 2 softening.
Yeah, it is only 2 softening lengths. But there's a bunch of stars that form there. So these have been really awesome questions. Are there any more questions? All right. Great. Thank you, everybody.